Hey there. Digital filters are kind of the unsung heroes working inside our phones, our speakers, you name it. They're designed with what should be mathematical perfection. But what happens when that perfect theory slams into an imperfect, physical computer? Today, we're going to dig into why a filter design that looks flawless on paper can end up completely broken in the real world. So that's the big question, right? It's this classic engineering puzzle where beautiful, elegant math meets the messy physical limits of a machine. And the answer, as you'll see, isn't just about the math. It's about how we choose to build the thing in the first place. Okay, so to get to the bottom of this, we've got to start with the absolute basics. Before we can see how a filter breaks, we need to see what it's actually made of. And honestly, you can think of them as the fundamental Lego bricks for all of digital signal processing. At its heart, a digital filter is really just a recipe. It takes a signal, say a digital audio track, and it performs a bunch of calculations on it. The goal is to change it in some useful way, like, getting rid of annoying static or pumping up the bass. Now, this is the part that's kind of wild. No matter how complex or fancy a digital filter gets, it's all built from just these three super simple parts. You've got an adder, which just sums signals up, a multiplier to make them louder or quieter, and a delay, which is basically a tiny piece of memory that holds onto a value for just a split second. That's it. So if those are our Lego bricks, the next logical question is, how do we snap them together? Well, engineers have different blueprints. We call them structures or architectures for arranging those adders, multipliers, and delays to get the job done. And these blueprints mostly fall into two big families. The difference? It all comes down to feedback. IIR filters are kind of like having a conversation with yourself. They take their own output and feed it right back into the input. It can be super efficient, but it's risky. FIR filters, on the other hand, are a one-way street. Data flows in, gets processed, and flows out. No feedback loops, which makes them way more stable and predictable. And you can see there's a whole menu of options. You've got common structures like direct, cascade, and parallel forms that you can use for both families. But then, for FIR filters specifically, you have these cool specialized forms like linear phase that give you some pretty neat advantages. Let's just zoom in on that linear phase one for a second, because it's a perfect example of some really clever engineering. It basically notices when the filter's math has a symmetrical pattern to it, and then uses that symmetry as a shortcut to save a ton of work.
And the payoff for being that clever? It's huge. By using that symmetry trick, this structure can cut the number of multiplications it has to do by almost half, compared to the most basic blueprint. In a world where every bit of processing power counts, that is a massive, massive win.
All right, so far, everything sounds great, right? We've got our simple building blocks, we've got these clever blueprints, everything is perfect. Well, perfect in theory. But now we have to talk about the real world. We have to introduce the glitch in the system that can make this whole beautiful design come crashing down. And that brings us right back to our big question. You see, our mathematical designs assume we can use perfect numbers with an infinite number of decimal places. But the computer that's actually running the filter, it just can't do that. This fundamental limitation has a name. It's called quantization. It's the process of taking a perfect, high-resolution number and basically squeezing it down to fit into the limited number of bits a computer can actually handle. It's always an approximation, a compromise between the ideal world of math and the real world of hardware. And this approximation usually happens in one of two ways. Truncation is the brutal approach. It literally just chops off the extra digits it doesn't have room for. Rounding is a little bit smarter. It looks for the closest value it can store. But either way, you're introducing a tiny, tiny error into your perfectly designed system. So, a tiny error. What's the big deal? You'd think it wouldn't matter much. Well, this is where things get really interesting, because we're about to see how those tiny, seemingly harmless rounding errors can pile up and cause a complete catastrophic system failure. And here is the absolute key to this whole mystery. Not all of our blueprints are created equal. The way we arrange those Lego bricks, the adders and multipliers, drastically changes how sensitive the filter is to these little errors. Some structures are tough. Others are incredibly fragile. The biggest offender by far is the direct form. It's often the most straightforward way to draw the filter from an equation, but it's famous for being super sensitive. This is especially true in really high-performance filters, where these critical mathematical points we call poles end up packed really close together. You can think of it like trying to balance bowling pins. If they're spread out, it's stable. But if you cram them all close together, the tiniest nudge can make the whole thing topple over. So, on paper, our design is a thing of beauty. A simple low-pass filter should have a high response for low frequencies, letting the bass through, and a low response for everything else, blocking it. Simple, clean, perfect. But then you go and build that exact same filter using that fragile direct form structure, and you get, well, a complete train wreck. The low end becomes unstable, the mid-range is just random garbage, and the high end is pure noise. Those tiny little rounding errors have snowballed into total failure. The filter is worthless. So what do? Do you just give up? Of course not. This is where the engineering comes in. If the math is right but the blueprint is wrong, the solution is simple. You pick a better blueprint, one that's designed to survive in the real world of imperfect machines. And this is the elegant solution. Engineers almost always prefer structures like the cascade and parallel forms. Why? Because instead of building one giant, complex, fragile filter, they break the problem down. They build it as a chain of much smaller, simpler, more stable sections. This keeps those sensitive poles isolated from each other and stops the errors from ever piling up in the first place. So when you look at it this way, the choice is pretty clear. The direct form might look simple on a whiteboard, but the cascade and parallel forms are the ones that actually work reliably. It's a classic engineering trade-off. You accept a little more complexity in the design to get a whole lot more robustness in the final product. So if you remember one thing from all this, let it be this. The how is just as important as the what. The structure you choose to build an idea is every bit as critical as the idea itself. In the world of digital filters, a perfect equation built on a fragile structure is just a recipe for failure. And that really leads to a bigger thought, doesn't it? This isn't just about audio or images. This whole idea of designing for imperfection, of choosing robust structures over fragile ones, applies everywhere in computing, from medical scanners to financial models. It's a powerful reminder that to build amazing things in our digital world, we have to be just as smart about our blueprints as we are about our math.